Welcome to this comprehensive guide on using generics in C#, designed specifically for beginner C# developers and Unity users. Generics are a powerful feature in C# that allow you to write flexible, reusable, and type-safe code. They enable you to define classes, methods, interfaces, and delegates with type parameters, which act as placeholders for specific data types. Introduced in C# 2.0, generics are now a fundamental part of modern C# development, widely used across various applications. One of the primary benefits of generics is enhanced type safety, which helps prevent runtime errors by catching type mismatches at compile time. This means your code is more robust and less prone to unexpected issues during execution. Generics also promote significant code reusability, allowing you to write a single class or method that can operate on multiple data types. This eliminates the need to duplicate code for each specific type, streamlining your development process. Performance is another key advantage, as generics avoid costly boxing and unboxing operations when dealing with value types. Boxing converts a value type to a reference type, while unboxing performs the reverse, both of which can impact application speed. Finally, generics greatly improve code maintainability, as you only have one implementation to manage for various data types. This makes updates and debugging much simpler and more efficient. Let's begin by exploring generic classes, which are classes that accept a type parameter within angle brackets. This allows them to operate on different data types, while strictly maintaining type safety. The specific type for the parameter is determined when you create an object of the generic class. Here's a simple example of a generic container T class in Visual Studio. This class can hold an item of any specified type T. Now, let's see how to use this generic class. We create an int container instance, specifying int as the type parameter. Then, we add the integer 42 to it. The console output confirms the integer stored. Similarly, we can create a string container by specifying string as the type. We add the string hello generics to this container. The output then displays the string held by the container. This demonstrates how a single generic class can be instantiated with different data types, providing immense flexibility. Next, let's delve into generic methods, which are methods that include type parameters in their signature. These methods allow you to write functions that can work with various data types without being tied to a specific one. Consider this findMax T generic method, designed to find the maximum element in an array of type T. The where T, IComparable T clause is a constraint, ensuring that T must implement the IComparable T interface. This constraint is crucial because it guarantees that elements of type T can be compared to each other. Let's see findMax in action with an integer array. We call findMax with inArray, and the compiler infers T as int. The console output correctly identifies 8 as the maximum integer. Now, let's use the same method for a string array. Again, findMax is called, and T is inferred as string. The output shows cherry as the maximum string based on alphabetical order. This illustrates how a non-generic class can effectively include generic methods by specifying a type parameter with the method name. Moving on to generic interfaces, these are interfaces defined with one or more type parameters. They allow you to establish contracts that can be implemented by various types, ensuring consistent behavior. Here, iRepository T is a generic interface defining common data access operations. This interface specifies a set of operations for working with entities of type T. The customer repository class implements iRepository specifically for customer entities. Similarly, product repository implements iRepository for product entities. This pattern ensures that both repositories adhere to the same contract while handling different data types. Now, let's explore generic delegates, which enable you to create delegates that work with various data types. They offer type safety and can improve performance by avoiding boxing and unboxing operations. Here, transformer T is a generic delegate that takes an input of type T and returns a value of the same type T. We define a square method that takes an int and returns its square, and a toUpper method that converts a string to uppercase. We assigned a square method to a transformer int delegate instance, calling square transformer with 5 outputs, 25. Then, we assigned a toUpper method to a transformer string delegate instance. calling upper transformer with hello outputs hello. This demonstrates how the same generic delegate type can be used with different data types, showcasing its versatility. Next, let's discuss constraints on generics, which limit the types that can be used as type arguments. Constraints are specified using the where keyword and allow you to perform more specific operations on the generic type. Common constraints include where t, class for reference types, and where t, struct for value types. Other useful constraints are where t, new for types with a public parameterless constructor, and where t, base class for inheritance. You can also use where t, interface to ensure a type implements a specific interface. Here, data store t is constrained to only accept reference types. This ensures that any type used for t will be a class, preventing value types from being assigned. Now, let's see how generics are applied in Unity, a popular game development engine. Generics are incredibly useful in Unity for creating reusable components and robust systems. They are commonly used for generic lists, dictionaries, and other data structures within Unity projects. A frequent use case involves creating generic methods to find components of a specific type on game objects. Here's an extension method getComponentInParent t for GameObject. The constraint where t, component, is vital, ensuring that t must be a Unity component type. This allows us to safely retrieve any component that derives from component. For example, to get a rigid body component, you simply call getComponentInParent rigid body. In Unity, constraints to monobehavior or component are particularly common and highly effective for game development. Let's briefly touch upon some advanced concepts related to generics. Variance, including covariance and contravariance, allows for more flexible assignment of generic types. Type inference enables the compiler to automatically deduce type arguments based on context, improving code readability. Reflection allows you to obtain information about generic types at runtime, which is useful for dynamic operations. Finally, let's review some best practices for working with generics. Always use clear and descriptive names for your type parameters, such as t-item or t-key, to enhance code clarity. Utilize constraints effectively to ensure type safety and enable specific operations on your generic types. Leverage type inference to make your code more concise and readable, letting the compiler do the heavy lifting. While powerful, use covariance and contravariance sparingly, as they can sometimes introduce complexity. By understanding and applying these concepts, you can write cleaner, more efficient, and maintainable C# code. Thank you for joining this guide on generics in C# for beginners. Keep practicing and happy coding!